Good afternoon to everybody. Welcome to the second session of today. I'm Eduardo Barrios, and I will be the chairman of these sessions. Our first speaker is Professor Alfredo Raya from Universidad Michoacana de San Nicolás de Hidalgo. Thank you for accept the invitation, and Professor Raya, you can start.
Okay.
The floor is yours.
Thank you very much. I would like to start by first thanking the organizers of this meeting for the invitation to participate in this very interesting workshop on topological quantum matter. And I will take the opportunity to present some of the ideas that we have been working in our group in these areas, where basically we are interested in the influence of the Chern-Simons term and its impact in the dynamical generation of fermion masses when fermions are restricted to a plane, basically through the electromagnetic interactions. Now, aiming to describe some materials like graphene and others, we are exploring the structure of these interactions through a particular version of quantum electrodynamics that has to do with a dynamical reduction of the ordinary theory, where electrons live in different dimensions than photons, and so we can explore what is the impact of these several ingredients that have in the generation of fermion masses. There are a number of ideas that motivated us to start this kind of research. First of all, quantum electrodynamics on a plane, or simply QED3, has been intensively studied for quite some time because it shares two very intriguing features of QCD. It exhibits chiral symmetry breaking and confinement, but because QED is an abelian theory, the structure of it allows to get deeper insight and what are the intricacies of the interaction that shed light of how these symmetries are breaking or restored, and what are the ingredients that are required in order to explore the traits of this phase transition. The result of this symmetry breaking, the dynamical symmetry breaking of the chiral symmetry, is observed as the generation of masses for the constituent quarks in QCD. And so understanding how these constituent quarks generate their masses through the strong interaction is one of the key ingredients that, or the major goals that heavy ion physics is pursuing nowadays, and that has been pursuing for already a couple of decades. So in that regard, QED3 serves as a toy model of QCD, because in these experiments, the high temperatures that form induce a dimensional reduction of QCD to a planar theory, where on top of that, the diagrams, the corrections, which are non-planar in QCD, are subleading, and thus QED3 can serve as a good starting point to explore the traits of chiral symmetry breaking in QCD. One of the frameworks that in which we can explore the symmetry breaking are the Schwinger-Dyson equations, which are the field equations of a given quantum field theory, which are basically a tower of relation among the Green's function of the theory. And these equations are non-perturbative in nature, and thus have the properties to address issues such as confinement, dynamical symmetry breaking, the formation of bound states, and so on. And within this framework, in QED, back in the 80s, there was a very interesting result by Appelquist and collaborators regarding a particular truncation, which shares a lot of information with what happens in QCD, is the 1/NF, where NF is the number of fermion families in the theory. When this number of fermion families is large enough, there exists a critical value above which chiral symmetry is restored. And this approximation is seen to have very important applications in high TC superconductivity and other condensed matter systems. So already this approximation, this truncation of Schwinger-Dyson has connections between the high energy physics realm of QCD, but also in the condensed matter realms through this system. Now, this approximation or this main result of the approximation in the leading order of the 1 over NF approximation has been seen to be a robust result when refined vertices, vacuum polarization effects, and other corrections, other more educated truncations of the Schwinger-Dyson equations are placed and are studied. So the conclusion nowadays is that there should exist a critical value of these fermion families above which chiral symmetry is restored in the theory, though the details, the precise details of the approximation might differ slightly on the value of this critical number. Now, on the other hand, planar systems are very interesting because of many features that they exhibit. For instance, quantum electrodynamics on a plane allows the inclusion of a Chern-Simons term in the gauge sector. And such a term induces fractional or anion statistics to the excitations. And it also is a source of parity and time reversal breaking. And that, namely, these discrete symmetries are broken if we take into account the effect of a Chern-Simons term in the gauge sector of the theory. The effect of such a term in the patterns of chiral symmetry breaking has been explored already for some time in QED3. And the observation, the main observation that has been put forward in the literature is that there exists a critical value of the Chern-Simons coefficient, which is, or the Chern-Simons angle, sometimes referred as theta, which also induces chiral symmetry restoration. So when we explore the traits of chiral symmetry, including vacuum polarization effects when a different number of families circulating in loops, plus the Chern-Simons terms, one can explore or study a critical line as a function of the number of fermion families and the Chern-Simons coefficient. And what is seen is the chiral restoration is a first order transition. So with these ideas, we were motivated to explore what happens in a theory which can describe the interaction, the electromagnetic interaction of electrons in graphene and related systems. Let's recall that the experimental realization, that the first isolation of graphene membranes back in 2004 puts QED3 in a more direct application, and more than a toy model, it has already a physical realization in some systems. And the point here is that besides the charge carrier were confined to a plane, the low energy behavior of such charge carriers is such that there is a linear dispersion relation, and these charge carriers carry a chirality degree of freedom. So when one goes to the continuum limit of a tight binding description of monolayer graphene, one ends up with an effective description in terms of the degrees of freedoms of QED3. And thus, this identification already provides or opens a possibility to explore some of the features that have been put forward in a high energy physics context, but to be explored in condensed matter and vice versa. So there is an opportunity through this theory to explore features of high energy or condensed matter systems within a same framework. Now, there are some issues that have to be taken into account. For instance, QED3 correctly describes what is the dynamics of charge carriers in graphene, but it fails to describe the interactions of electrons and external electromagnetic fields. Basically, for instance, the static interactions in ordinary QED3 correspond to a logarithmic potential and a logarithmic behavior of the static potential. But in graphene, we know that we have to have this Coulomb form of the static interaction. So the theory, the dimensionally reduced theories in standard matters, is not capable of describing properly this interaction with external magnetic fields. And basically it's very well understood because experimentally, the external electromagnetic fields are objects that live in space, but the charge carriers of graphene are restricted to a membrane. And so one already sees the necessity, the need to consider mixed dimensional theories in which the external fields and the matter fields live in different dimensions. And this realization has been already discussed in literature in some features. And basically, the idea is to describe the electromagnetic fields as if they live in space, I mean, in 3 dimensions, but then restrict the interaction of these fields to the matter fields that live exactly in 2 dimensions, precisely in this sheet, which we can identify with the third component set to 0. These ideas have been discussed already for some time. The first ideas came by the group of Marino in Brazil, that they introduced fractional powers of the Lambertian operator, and they exploit this mathematical structure to also include the Chern-Simons into the description. And they refer to this framework as pseudo quantum electrodynamics of PQED. And a few years later, and independently, the Ukrainian group by Valery Gusinin and co-workers developed a similar framework, but based on brain world scenarios, where the analogy was that instead of the gravitational field living in more dimensions, they claimed that it was the gauge fields that live on space, but the matter fields were restricted to a brain, in this case, to a plane. And they dubbed this theory reduced QED. So there, we simply adopt both the names, and we refer to this theory of PRQED, and we are referring to this theory where photons live in 3 dimensions, but fermions or electrons are restricted to a plane. And with this theory, there are some things that have to be taken into account when we want to explore the traits of dynamical symmetry, the dynamical chiral symmetry breaking within this theory. So for us, the goal was to investigate how, first of all, how chiral symmetry can be broken in this theory, and what is the influence of the Chern-Simons terms, if at all, in the description of the symmetry breaking. The point is that this reduced QED or pseudo QED shares a lot of features with ordinary QED in 4 dimensions. We know that the ordinary QED, the coupling is dimensionless, but if coupling exceeds a critical value of pi/3. And it is seen that this mass that is generated has a behavior or a scaling in which the more intense the coupling is as compared to this critical value, the more mass can be generated. And this is known the Miransky scaling law, and corresponds to the critical value of the coupling precisely corresponds to an essential singularity in this scaling, in such a way that we say that the chiral symmetry is broken in QED4 through a conformal phase transition. So when people started to look at the same scenarios in reduced QED, they find out that the Brazilian group basically find out that the same scenario happens in reduced QED, but of course the value of the coupling is different. In this case, is pi/8, and the same assumptions were basically made in order to truncate the Schwinger-Dyson equation. So if we don't take into account the Chern-Simons term, what we need in order to break chiral symmetry in reduced QED is to have a coupling that exceeds this critical value. Next, in order to see how to explore this framework and how the Schwinger-Dyson equation look like in this theory, let us recall how we can define this theory. What we can start from is from the ordinary action of QED in 4 dimensions, which is basically the Maxwell term and interactions of these electromagnetic fields with the current, and some gauge fixing, which we can choose in many ways in this action. And the point is that this current should be defined only in a lower dimensional brane, in this case, on a plane through a delta function that is restricted to the third component of the spatial coordinates in this theory. And so we have, when we insert this current over here, what we can do is simply add the dynamics of fermions, but by adding a kinetic term of this form. And now we have that, let me come here. We have 4 dimensions for the electromagnetic fields, but 3 dimensions for the fermion fields. And the way to proceed to a dimensional reduction is as follows. We have first to integrate out the 4-dimensional gauge field, and then we integrate the third spatial direction in the case of these gauge fields that are in this action. And then we will have an effective gauge field which lives and interacts with the fermions on the plane, where the new field is precisely constrained again to this membrane of 2 dimensions. As a result, the corresponding effective action looks like this, where instead of the standard Maxwell term, we have here the square root of the D'Alembertian operator that comes here, and it is the way the Marino group proposed the action of this theory in this form. Obviously, here we have the electromagnetic fields tensor, and the gauge field comes here in the covariant derivative. Psi are the fermion fields that for this framework we choose to be 4 components, and the gauge fixing part comes at the end here in this part. We already see that this theory is highly non-local, but it has been shown by several groups that it respects causality, and moreover, the Green's functions of this that we can derive from this action are well-defined, well-behaved functions. And thus one can try to read out the Feynman rules for this theory, and then simply follow these Feynman rules in order to set up the Schwinger-Dyson equations for them.
Well, I'm sorry, one question, please.
Yes.
Your indices mu nu then run from 0 to 3. The index?
No, when we end up here, the Greek indices run from 0 to 2.
Yeah.
Because these indices correspond to the coordinates on the plane of motion of the electrons.
But then your electric field doesn't live in 4 dimensions, as you said it should.
Okay, so here I should have written different indices. Let me say that again. When I write these indices in this 4-dimensional integral, I will split the mu equal 3 part, and then I will end up with a new set of non-trivial indices that come here.
Yes.
All these run from 0 to 1.
Yes.
But when I write the corresponding equation in here, now these indices, because they run only on 3 space dimensions, are constrained to take the value 0, 1, 2.
0, 1, 2. But so the electromagnetic field live in 3 dimensions.
The electromagnetic field here, because it is already dimensionally reduced, it only lives in 2 dimensions. And also the gauge field that appears here in the covariant derivative lives in 2 dimensions. Yes. All the objects in this action are restricted to 2 dimensions.
2 dimensions, yeah. Okay, thank you.
Okay, now you're welcome. So out of this action, the corresponding Lagrangian is very similar to the ordinary Lagrangian of QED, except for the Maxwell term that now has this form. And this particular form makes explicit the behavior of the photon propagator, which is different in this theory. Instead of having the standard 1/q squared that we find when we allow the fermions and photons to start in the same dimensions, it has a 1/q simply, and so the infrared divergence is softened in this case. Now, if we fix the gauge covariantly, we should take into account that the covariant gauge parameter of the plane is not the same covariant gauge parameter of the space. So I use a different symbol in this regard. And the fermion field is basically, the fermion Lagrangian has basically the same form. And so the propagator in this case is a standard in form, and I am considering massless fermions to start with. We don't consider here the possibility of having mass so far. Now, these are the three-level propagators, and we need them because we will, on top of that, on top of this action, consider as well the Chern-Simons Lagrangian. Now, this Chern-Simons Lagrangian, when we are living in a plane, is basically this object that appears in here that is the analogous of 4 dimensions, because it is the product of the F, the stress tensor and its dual. So this is the Chern-Simons Lagrangian, and we can notice here that this Lagrangian remains unchanged, a part of a total derivative of space-time when we perform a gauge transformation. And so the corresponding action is a gauge invariant, but this action actually breaks parity and time reversal. So this should be somehow reflected in the dynamics of fermions. And basically here is to recall how we introduce the Chern-Simons action in 2+1 dimensions. In QCD, for instance, we start with the product of F and F dual, and this is the Chern-Simons term, the topological theta term, and that is why the nature of the topology in QCD can be inherent to a 3-dimensional space. But this 4-dimensional Chern-Simons term, when constrained to a plane, is basically this object, and this is because this contraction of the Levi-Civita and A mu is the definition of the dual tensor on a plane in this form. So when we consider the Chern-Simons term, besides the modified Maxwell term that appears in here, we should also have this tensor that is characterized by this Levi-Civita symbol that appears in here. And this Levi-Civita, what actually makes is we continue with the softening of this pole in the transverse part of the propagator, but it also adds this new term into the propagator, which already is explicitly representing parity and time reversal breaking in this part. Now, if we simply make a dimensional analysis of the terms of this Lagrangian, we will find that this theta parameter in reduced QED is dimensionless. In ordinary QED, it has a dimension of a mass, and it is actually a topological mass that we can associate to the gauge bosons on a plane. But in this case, being dimensionless, it does not correspond to a topological photon mass. And we use this notion simply of topological theory by historical reasons. It's not necessarily the case that it has this non-trivial topology included in the dynamics. And this is because this theory possesses a remarkable property that is scale invariance. So with these ingredients, once we know the Feynman rules, we can simply write down the corresponding Schwinger-Dyson equations. For the 2-point functions, basically these equations describe how the self-interactions, here the self-interaction of the fermion or the self-interaction of the photon, modifies the propagation properties of these particles, and in any case, they could have, or they encode the possibility of chiral symmetry breaking. I am not going to the details explicitly of these equations, but the general solution of this equation is a propagator that has two unknown functions, A and sigma over here. And this is the first part is related to the wave function renormalization, and the second part is related to the mass function of this object. For massless fermions, this self-energy would be, or this mass function would be equal to 0. But when this acquires a finite value, we say that masses are dynamically generated for these fermions. One starting by commonly and widely used starting point is to truncate the Schwinger-Dyson equation at the rainbow ladder level, where we neglect the wave function renormalization effects, and thus we have that this equation 13 is actually a self-consistent equation for the mass function, which is this integral equation over here. This integral equation is a nonlinear integral equation, but it has trivial solutions. Sigma equals 0 is a solution of this equation. But we will find that if this value of the coupling, this alpha over here, exceeds a critical value, we can, in fact, find non-trivial solutions to this nonlinear equation. This equation has been explored for quite some time in literature. And actually, when we write the corresponding equation in ordinary QED, it has basically the same form, except that the coupling constant has a different meaning in QED3 and in reduced QED. In QED3, this coupling actually has the information of the number of families that are circulating in loops that lead eventually to chiral symmetry restoration. And here, the coupling is basically the intensity, the strength of the electrostatic interactions in reduced QED. And so one can map the criticality of the fermion, the number of fermion families to the criticality of the value or the strength of the coupling, and vice versa, in order to have information of the solutions of this equation. Now, this equation was first solved back in the 80s, but so the solutions are well known, and they say that if this NF exceeds some critical value around 3, then chiral symmetry in this theory should be restored. Now, the thing is that when we have the Chern-Simons term, and we consider fermions, it is much better to consider the chiral projections, and we will define the right and left-handed fermions through this chiral projector, where this projector is basically the commutator of gamma 3 and gamma 5. And this is, it appears because in the Dirac equation on a plane, we only need gamma 0, gamma 1, and gamma 2 to write down the Dirac equation. So we have gamma 3 and gamma 5, which are matrices that all of them anti-commute with these matrices, and so the chiral projector can be generalized to have this form. And being a projector, of course, it has these properties that are shown in here. Now, what is the difference to have these left and right-handed fermions? That we can associate to them two different types of mass terms. The ordinary Dirac mass term can emerge, and it will eventually be connected to the solution of the gap equation, a non-trivial solution of the gap equation, and it is the ordinary mass term that is generated in QED3. But on top of that, there is another mass term, which is known as the Haldane mass term, that can also be generated. Now, the symmetries of these two bilinears that appear in here are completely different. This term, this mass term in the Lagrangian, is parity and time reversal invariant, but it breaks the chiral symmetry. On the contrary, the Haldane mass term breaks parity and time reversal, but preserves chiral symmetry. And so the most general form of the Lagrangian that one can consider is this, where the mass terms, the Dirac and Haldane master terms appear explicitly in the Lagrangian. But there is one problem, because although the solution to the Schwinger-Dyson equation has now two wave function renormalization and two mass function, none of these correspond to poles on propagators. So what we actually need to do is to make use of these projectors and write the Fermi-Lagrangian in terms of the left and right-handed fields, where these are already identified to have these poles, which are combinations of Dirac and Haldane mass terms. And one can see a very interesting feature here. If we have Dirac fermions, and then we add on top of that, the Haldane mass, we will see that one species is heavier than the other. And so the generation of masses in this case is expected to be of the following form. The more the Haldane mass is generated, one species is very heavy and the other is very light. Well, with all these observations, what we have is that the UAB equation, or the Schwinger-Dyson equation, can be cast in this form for a given chirality or projection of the fermion fields that comes here. And so these are the forms of this propagator, and following the standard procedures of taking traces and simplifying and so on, we end up with a non-linear integral equation for the mass function of each chirality. And these systems are completely decoupled, so we can solve the left and right sectors decoupled. And what we observe here is that there are two parameters in the gap equation that we can take into account: the coupling and the Chern-Simons. And when we do that, we can observe what are the behavior of this mass function as a function of these two parameters that come here. One way of proceeding in this form is simply to linearize the equation and convert it to a differential equation, which has this form. Is an inhomogeneous equation of second order that has this form here, and it is subject to these boundary conditions that appear here. One can solve this differential equation exactly, and it has two components. The first component that comes in here is the part or the piece that gives rise to a Miransky scaling law, provided this term is not present there. But then the presence of this term comes as what are the deviations precisely of this scaling that appears here. Now, in the Miransky scaling law, it appears the critical value of the coupling to pinpoint what is the essential singularity that required to have a conformal symmetry breaking to generate the masses. And now this critical coupling depends on the theta coefficient in this form. And this appearance of this coefficient in here resembles to have an effective dielectric constant in the medium induced in the framework, induced precisely by this Chern-Simons term. Okay, so let me just show you what are the actual numerical solutions to the mass functions. And what we are doing is we will start with a coupling, which we know is above the critical coupling, so that we can have a non-trivial solution. And what we are doing here is to incorporate the influence of the Chern-Simons term. Here, the green curve corresponds to the case where there is no Chern-Simons. And then we see that as this coefficient increases, the height of this mass function increases. The height of this mass function is related to the amount of mass that is dynamically generated. So it says that at least for this right, or for this chirality m minus, the mass is increasing as the theta coefficient is increasing as well. But if I observe the second chirality, the scenario is completely different, because we now have the higher curve, the higher plateau for the mass function when there is no Chern-Simons term, and as we increase the value of the Chern-Simons term, the height of this mass function, namely the amount of mass that is being dynamically generated, is lower and lower. But then suddenly there appears a critical value of this coefficient when actually the height flips sign, and then the mass function becomes negative at zero momentum. And here, this behavior is a signal of some phase transition that is occurring in the system. And this phase transition, let me show you next, will be associated to the chiral restoration. Basically, what we have here is what is the value of the height of this mass function that flips sign as a function of this coefficient that measures how high above the critical coupling we are solving the Schwinger-Dyson equation that comes in here. And the discontinuity comes here because this corresponds to the critical value of this theta parameter where the transition is occurring. And so far, I am just saying that it is a transition, but I am not explaining yet what actually is happening in terms of chiral symmetry. This is the corresponding plot to the second chirality, the chirality that grows bigger and bigger, and we observe a very smooth behavior with no discontinuities here in the evolution of the height of this of the mass function of this chirality. Now, when we put one on top of the other, we observe that these two start degenerated. The Chern-Simons term, what actually does is to split this degeneracy to have one species that has a larger mass and one species that has a lighter mass. But in absolute value, we have here the dots that appear in here, and we observe that actually at this point, both these masses are of the same absolute value. And when this happens, what we have is that the chiral symmetry is being restored, and basically is because of that. If you recall, M plus is the sum of Dirac mass and Haldane mass, and the M minus is the subtraction of Dirac mass and Haldane mass. So when these guys are the same in strength, it means that the Dirac mass is no longer there. And what we only have is that the Haldane mass continues being dynamically generated. So this is, for instance, when we, instead of working with the chiral projections of the fermions, we work directly with the Dirac mass, and we observe here this fallout, this discontinuity that appears in here when it says that the discontinuity or the flip of sign is associated to the restoration of this mass. This fallout is basically connected with a symmetry being approximately restored in this case. And this is the case for the Haldane mass, and this continuity is appearing here still, but this Haldane mass is always being generated regardless the size of this parameter that comes here. So what we have done with this exercise is that we have investigated the role of the generation of Dirac and Haldane masses in reduced QED under the influence of a Chern-Simons term. And what we are observing is that whereas the Dirac mass could not be generated by some specific coefficient of the Chern-Simons term, the Haldane mass continue being generated for all values of this theta parameter. It means that one chirality of fermions that is in our description of the theory has a larger mass, and the other has a lighter mass that come in here. What we have observed is that with a suitable truncation of the Schwinger-Dyson equation, we can generate both masses, Haldane and Dirac, provided two things. We are above a critical value of the coupling to start generating masses, but below a critical value of this effective dielectric constant that suppresses the generation of masses. So this coefficient is actually its effect is as an effective dielectric constant that comes in here. So there is a competition in the dynamical generation through these two terms, the ordinary, the Maxwell term, and the Haldane, the Chern-Simons term, that can be measured as how much of Dirac and Haldane masses are being generated. Now, for large enough theta, the chiral symmetry is finally restored. And so the Haldane mass is still finite even if we reach this critical value. So the breaking of parity persists for all the values of this parameter that we consider in this work. Now the discontinuity that is shown in this transition reveals that the chiral symmetry restoration is of first order in the theory. And for us, it is relevant because we can connect this observation with the generation of chiral currents in planar materials. And again, I will make a connection with what happens in the dynamics of quantum chromodynamics is this effect, the so-called chiral magnetic effect, which initially was proposed to take place in the quark-gluon plasma, and that has not been observed in experiments of heavy ion collisions, but it already has been observed in three-dimensional Dirac materials. So in the quark-gluon plasma, it is argued that the quantum anomaly is responsible for precisely this imbalance of chiralities originated from topological configuration of the gauge fields. So there could be a connection of this effect if we continue to if we allow the Chern-Simons term to play a role in the dynamics of electromagnetic interactions of fermions in these two-dimensional materials. Because in these materials, the chiral anomaly is neatly generated, applying, for instance, simultaneously an electric and a magnetic field that point in the same direction. So we believe that this contribution has an impact in two sides. First of all, it continues to provide a toy model to investigate the effects of anomalies in chiral symmetry breaking of QCD, but in a more friendly environment. And on the other hand, it could also serve as a model to look for materials where the masses that are being generated in these materials resemble precisely the interaction that could happen via the electromagnetic interactions of quasi-particles in two-dimensional systems. So thank you very much for your attention.
Okay, thank you, Professor Raya, for the interesting talk. We have time for questions. Are there any questions from the audience?
So I have just a little question.
Go ahead.
So at the beginning, you show a Lagrangian, which is a contraction of the Maxwell tensor, but in the middle, you have an operator.
Yeah.
And you mentioned the causality is okay, but what happened with unitarity? Which is
it is also preserved in this theory. There are some works that address this issue, and that is, even though it looks highly non-trivial because of this term, but at the end of the day, the Green's functions are well behaved, and one can make use of all these Feynman rules framework to calculate some observables in reduced QED.
Yeah, yeah. Also, at the end, you mentioned about phase transition, which is of the first order, but this is non-topological, right?
Because this is this is non because there are a couple of comments in here. First of all, in this case, this theta parameter is dimensionless. So the theory itself doesn't have this topological property that ordinary QED3 has. But what we say is that the effect of this parameter, again, is physically as if it was an effective dielectric constant, and that is why it drives a discontinuous transition that is associated to a first order one.
Okay, is Landau phase transition, right?
Yeah, yeah.
Okay, thank you.
Are there any other questions? Luis, go.
I'm sorry, yeah. Okay, Alfredo, I saw that at the beginning you mentioned that it was that electric and magnetic field live in let's say three dimensions, no, and that was important for, I mean, for taking them properly into account. Okay, but then now you have, I insist in that, that you have F mu nu that goes 0, 1, 2. So for example, you can have only one magnetic field, which is F 1, 2, which means magnetic field in the direction, in the Z direction, let's say. So you're not allowed to have an arbitrary electromagnetic fields with these restrictions.
Okay, now if you have if you start with a theory where fermions and photons live in the same dimensions, what you are saying is actually correct, because in that case, the F mu nu would have only a magnetic field that points perpendicularly to the plane of motion of electrons. But in this theory, what we do is we take the ordinary three-dimensional electromagnetic field and we integrate non-perturbatively the third component of this electromagnetic field. And thus we are left with the effect of this bigger object, but restricted to a plane. And it can be seen because the behavior of the photon propagator is not as it is in the standard theory, where it comes as a 1/q square, but is rather a 1/q. Maxwell's equations are slightly modified in this connection. And what is the effect of the day at the end of the day? Well, you can have an external electromagnetic field of the configuration that you would like to, but when you dimensionally reduce this electromagnetic field, it would have a dressing here in the propagator.
But then tell me, how do you represent a magnetic field in the X direction, for example? So I don't see.
No,
so
yeah, I know.
This F mu nu, I mean, a magnetic field in 4 dimensions, how is mapped into this F1, to which F in your theory correspond a general, for example, magnetic field in 3 dimensions?
I don't have the exact form in which you map a constant magnetic field that points in the X direction in space to the same object, but where this X dimension is precisely the plane of motion of electrons. But what you can think of is, imagine you have the dynamics of this object, and you start squeezing the third spatial dimension until you have a slab, for instance, of some width, finite width that you have here. And then you can see the dynamics of electrons under this boundary conditions, and then eventually you would like to see what is the effect of taking this width to 0. This is as far as I understand, it's not a simple task to do that. It's not a simple visualization that you have in here.
Okay. So the main point to remember is that your F01s, 02, 13 are not related to the standard understanding of
exactly
of the electromagnetic, means other things. Okay.
It is a different thing. That is, it's an effective description of a magnetic field, but restricted to a plane. Yeah.
Okay. Okay. Comes
in
a mixed form, maybe. Yeah. Okay.
Yeah. It's not that the components are or the magnetic field alone or the electric field components.
Okay. Yeah. Okay. I last question. I got mixed by your definition of the restoring of chiral symmetry when M plus is equal to M minus. As far as M plus is M Dirac plus M Haldane, ¿no es cierto?
Yes.
And M minus is M Dirac minus. So if they are two are equal, the Haldane mass must be 0, not the Dirac mass.
But recall that there was a mass flip before. A sign flip before, yeah, and that actually kills the ME and leaves the MO.
Okay, well, thank you very much. Yeah.
Okay, welcome.
Okay, there's another question from Omar. Omar.
Yes, looking at the Lagrange that Professor Luis asked to you, I only would like to ask probably a silly question if it is worth to study this theory also, but in a lesser dimension, for example,
In low dimensions.
Yes, and what could be if it is worth it to study, or
It is. I mean, if you can dimensionally reduce a magnetic field, not only one dimension with respect to the plane of motion of electrons, but also you can do that too, and you could have like a wire where electrons are moving, but the external electromagnetic field is living in space. You can do that. Actually, you actually can do that. What I am not sure at this moment is whether you would have a Chern-Simons term of this form. Maybe the Chern-Simons term that you can add is a trivial one. I mean, one that is a full derivative.
okay? And do you know in which way does the contraction of the Faraday tensors would one would obtain? Because from this part, there's this interesting, or also
I could if you let me know your email, I could send you some references because I don't have the exact expressions off the top of my head, but yes, there are studies about what happens when you, instead of a plane, you have a wire, for instance.
Okay, perfect. Thank you.
Okay, very good.
Okay, thank you. Mauro also have the hand.
Okay, thank you. So maybe one silly question. Would it make sense to consider other non-local operators as the one there between the Fs, but between F and F dual?
Well, yeah. I think that this Brazilian group that put forward this kind of interactions also have considered non-trivial forms of the Chern-Simons term, where you can add these other operators in the parity violating part of the gauge action.
Okay, so because yeah, maybe it's not the simplest idea to work on, but given that we went crazy with this D'Alembert down there, why not going completely
to yeah
completely wild? Yes, okay.
Yeah,
but you say they consider it, so it's not
they have considered some I don't know exactly what is the actual problem with the boundary conditions that we have to impose in order to get reasonable solutions to the equations of motion, no?
Okay, yeah, makes sense. Thank you very much.
Okay.
Just a last question.
Okay.
So you talk about flipping the mass sink, M plus and minus, but how do we understand this flipping of the mass sink? For example, in the Haldane model, this is related with spin orbit coupling. Some physical mechanism which can flip the sink of this mass, which is different.
Now here the only I mean, when we have already because we have a full relativistic interaction, electromagnetic interaction between the electrons in here. So it is this electromagnetic interaction, which already includes the spin orbit and other corrections that are taken into account, that drives this sign flipping in this case, no?
Okay. Thank you. Thank you.
Okay, very good.
Okay, well, just probably a naive question. What is the physical meaning of the mass, the Haldane mass? Yes.
That is a very good question. In these models, as far as I remember, it is related to some magnetic flux coming through the unitary cell in this hexagonal lattice array. But because we are here going to the continuum limit, I lose contact with this particular idea. I have to think. But what I know for a fact is that whenever you have a Chern-Simons term, and the strength of the Chern-Simons coefficient is theta, you automatically generate a corresponding mass for the fermions, which is of the same intensity, the same magnitude, but related precisely to a mass that breaks parity, and then you can associate it with this Haldane mass. So what is the meaning, or what is the effect of the physical interpretation of the theta coefficient in QED3 would be translated to what is the coefficient what is the meaning of this coefficient in the case of the fermions, no?
Okay, well, thank you. Anna also has the raise the hand. Anna?
Hi. No, it's just a very quick comment about the question that someone just asked. This related to spin-orbit coupling. What we want to show here is that this kind of mass structure or gap structure, if you prefer, is usually associated to spin orbit, like this time reversal symmetry, right? So what we want to show is that maybe interacting with external fields, you can generate the same thing. That's the main point. So the Chern-Simons term can be associated to a certain configuration of electromagnetic fields. It's like electric field parallel to magnetic field. And we want to explore if this kind of structure can also be generated with interaction with external fields. So that's the point here. So since spin-orbit coupling is not always present, and in many materials you have like it's not significant, the spin orbit, so we want to explore if we can replace it by this kind of interaction.
Yeah. Okay. Thank you.
Okay, the last question, Saul.
Yes, thank you. So if I understand right, Alfredo, you start with a coupling that is high enough to already break chiral symmetry, and then you change the size of the Chern-Simons parameter to restore chiral symmetry, right?
Yes.
So my question is, what happened, or do you check what happened if you start with the case when you have a coupling that is not high enough to break the chiral symmetry, and if you just increase the Chern-Simons, there is another phenomenon that happens there, or it's just staying the same all the time?
The Haldane mass that you generate, okay, if you don't have a strong enough coupling, you won't be able to generate the Dirac masses. All you can get are Haldane masses. And when you start varying the Chern-Simons coefficient, you have only generating this Haldane mass until you reach the point where you can generate both of them.
No, sorry, can you repeat that last part? So
so if you all are always under the critical coupling so if you always remain in the subcritical regime of the coupling, you would only perturbatively generate the Haldane mass all the time, and you won't be able to generate any Dirac mass whatsoever.
Yes. So you won't see anything interesting or say about.
Well, it is already interesting, but you won't see. But you won't see a more intricated phenomenon happening here. Mm-hmm.
No, thank you.
Okay, we thank the speaker, our Professor Raya,